Hi everyone. In this part, we are going to learn method C for finding the modular inverse using very famous theorem that is called Fermat's little theorem. This method is super easy when the modulus is prime. What is Fermat's little theorem? The theorem says that this method only when the modulus is a prime number. The theorem says a raised to p minus 1 that is congruent 1 mod p. If p is prime and a is not a divisible, p rearrange to get the inverse. If we divide both sides by a, the equation become a raised to p minus 1 divided by a that is congruent to 1 by a mod p. Rewrite the equation a raised to p minus 2 that is congruent a raised to minus 1 mod p. That means inverse of a mod p that is equivalent to a raised to p minus 2 mod p. So, the formula for the modular inverse is a raised to minus 1 that is congruent to a raised to p minus 2 mod p. It is used only when p is prime. Now move on the example. Find inverse of 5 mod 13. Here a will be act as 5 and p will be act as 13. 13 is prime. Using this formula, a raised to p minus 2 that is congruent to a raised to minus 1 mod p. Apply these values. A will be act as 5. 5 raised to p is 13. 13 minus 2 that is congruent to 5 raised to minus 1 mod 30. So, we need to rearrange in our equation 5 raised to minus 1 that is equal to 5 raised to 11 mod 30. So we need to compute 5 raised to 11 mod 13. Then going to the another step that is used to repeated squaring method. It is a fast method. In this case, we compute the powers. First one is the first square. Here 5 square equal to 25 that is congruent to 12 mod 30. Then 5 square equal to 25 we apply divide 25 by 13. Then 25 equal to by using the division formula 25 equal to 13 into 1 plus 12. In this case the remainder become 12. So 5 square is congruent to 12 mod 13. Then move on the another square that is the 5 raised to 4. 5 square the whole square that is the 5 raised to 4. In previous step we found that 5 square equal to 12. Therefore 5 squares to substitute the 5 square value that is equal to 12 the whole square. Then value become 144. Now reduce 144 mod 13. That is 144 is divided by 13. Then the remainder become 1. So 5 raised to 4 is congruent to 1 mod 13. In this case, the grade found method. Then 5 raised to 1 equal to 1. That is 5 raised to 1 that is congruent to 1. Then going to the another step that is the break the exponent 11. That means break the power of the 11. In this case we want to 11 in terms of by using the decomposition. Here, the decomposition means breaking a number into the smaller convenient parts. Suppose we have to using two methods can be performed in decomposition. First method is break using simple addition. Normally 11 can be 8 plus 2 plus 1 because 8 plus 2 equal to 10, 10 plus 1 equal to 11. Here we just choose convenient parts that adds up to the 11. Then another method for the decomposition, that is break using power of 2. That means find the powers of 2 less than or equal to 11. That is power of 2 equal to 1, 2, 4, 8, 16. That is less than 11. In this case, we stop at 8. Then now subtract step by step. First we have to subtract 11 minus 8, that is equal to 3. Again choose powers of 2 less than 3. In this series we stop the 4. That is we take the value 2. That is 3 minus 2 equal to 1. Again remaining is 1. That is take the 1. So in our decomposition 11 equal to 8 plus 2 plus 1. Then move on the Fermat's little theorem. In this case, we have found the three equation, that is 5 raised to 4 congruent to 1 and 5 square congruent to 12, 5 raised to 1 congruent to 5. Now we express 11 as decomposition, 11 equal to 8 plus 2 plus 1. So 5 raised to 11 will be act as 5 raised to 8 into 5 raised to 2 into 5 raised to 1. Now evaluate each part. 5 raised to 8 equal to 5 raised to 4 the whole square. In this case 5 raised to 4 will be act as 1. So that is congruent to 1 square equal to 1. Then 5 square, that is congruent to 12. 5 raised to 1 is congruent to 5. Then multiply in our 5 raised to 11 equation. 5 raised to 11 equal to 5 raised to 11 congruent 1 into 12 into 5. The value become 16. Now reduce mod 13. Then 16 equal to, by using the division formula, 13 into 4 plus 8. The remainder become 8. In this case 5 raised to 11, that is congruent to 8 mod 3. So the inverse, the 5 raised to minus 1, that is congruent to 8 mod 13. Here in our equation 5 raised to 11 mod 13, in 5 raised to 11 value become 8. So our equation become 5 raised to minus 1 congruent 8 mod 13. Find the verification process to check 5 into 8. That means 5 raised to minus 1 to represented as 1 by 5. That is equal to 8 mod 13. So to apply 5 into 8, that is equal to 14. 14 is divisible by 13. So in this case 14 is divisible by 13. That is remainder become 1. So 14 is congruent to 1 mod 13. So the inverse of 5 mod 13 is 8. So our equation will be correct. That's all for method C. We learn how to find modular inverse using Fermat's little theorem, which works beautifully when the modulus is prime. Where do we use Fermat's theorem and modular inverse in real life? By using the digital signature like the online transaction, then using encrypted communication, for example, our WhatsApp, Google Pay, banking apps, etc. Then real life another example is the public key cryptography by using the RSA algorithm. In this system, you need to compute inverses of very large numbers and modulus is often a very large prime. Fermat's little theorem makes inverse calculation much faster. So every time you send a money online, logging securely or use OTP, this method helps to secure your data. And that's all for today. We learned how to compute modular inverses using Fermat little theorem with a simple example and even a real life connection. In the next video, we will explore Euler's theorem, which is the general version of Fermat's method when the modulus is not prime. Thank you for watching.